R here. Wow. Let's start. Mark your own, please. I guess it wouldn't be right if I didn't start this internet video with a special shout out to my 7 students who didn't do the quiz and are now sitting in the hallway. Oh, I'm thinking bad thoughts about you right now. So when you're watching this at home, stop, pause the video, smack yourself on top of the head, and then keep going. Here we go. Energy is the ability to do work. 1 mark. What is the minimum amount of work it would take for a 55-kilogram student to climb a 6-meter high flight of stairs? I'm going to, just to speed things up a bit, I'm actually going to go through my answer key that I've pre-made. Normally I walk through all, oh, that's momentum, that's next unit. And I want quiz 2000 answers. So it's going to be force times distance. Which force when you're climbing stairs? Gravity. mg, which distance, h, and in fact, that's where our potential energy equation came from. You get 6,234, 6.23 times 10 to the 3rd joules. Number 3, a 2-kilogram ball is 5 meters above the ground and is falling at 5 meters a second. What's its total energy? I haven't asked you this. Total energy, what do you think that would be? Hey, I bet you that would be the potential plus the kinetic. And I think I can just add them, Megan, because they're scalars. No vectors, no fancy tip to tail, just add them up. So I said it's going to be the kinetic plus the potential. It's going to be a half mv squared plus mgh. And holy smokes, I got 123 joules. Number 4. Using the following graph of force versus position, find the total work done. Now, I can't go force times distance. The reason I can't, Dorothy, can you see the force is changing? It starts out at 0 and it ends up at 200. Force times distance only works for a constant force. So that was our first definition of work. Our second definition of work was the area under a force versus distance graph. Oh, I think that's where I'll use this one. Boys and girls, I like this question and number 5. I like this question and number 5. I like this question and number 5. I guarantee one of your written questions is going to ask you to do something, finding the amount of work from a graph, and then do something with it, also cluing in that that work must have gone into changing potential or kinetic energy or something. Anyhow, I divided it up into a triangle and a rectangle. The area 1 of the triangle is base times height divided by 2. Area 2 is length times width. The base, 200. Sorry, let's try that again. The base, 3. The height, 200 divided by 2. And length, 200. I got 700 joules. Okay? Now, I'm assuming this is somebody pushing an object, and they applied an increasing force for the first 1, 2, 3 meters, for the first 1, 2, 3 meters, and then they hit their maximum speed, and now they're just applying a constant force. But you know what they've done? They've caused this object to speed up. How do I know? Because that energy had to go somewhere. I think it went into kinetic, which means if I tell you the mass of the object, and if I tell you that we started at rest, or the initial velocity, whatever it is, you should be able to figure out the final velocity, much like number 5. So in number 5, if the graph in question number 4 represents work done, find the speed. The fact that they said speed, Dorothy, is a hint I want to use a scalar approach. Otherwise, they probably would have said velocity. I can say that work is change in kinetic plus change potential. Paige, did they mention like a changing height or anything? I think they would have if we assume level floor. So I said it's a change in kinetic. The initial was 0. The final is a half mv squared. And I know how much work was done, 700 joules. Solve for v final, and you get 18.7. Number 6. This one was a bit of a twist here. They gave me a lovely picture. I said, what's the power? Power is work over time. Power is force times distance. I said, how much time? Ah, they were sneaky, John. Instead of giving me the time as a number, they gave it to me as an English word, a minute. I said, ha, 60 seconds. How much mass? Well, in 1 minute, we move 20 people, 60 kilograms each. The total mass is 20 times 60. Oh, what force? Gravity, mass times gravity, mg. Times distance. The other way you could have done this is you could have said, well, if I'm moving 20 passengers a minute, how many passengers is that? How many seconds is that for 1 passenger? 20 passengers a minute. How many seconds does it take for one passenger? 20 passengers a minute, 20 passengers in 60 seconds. How many seconds does it take for one passenger? 3 seconds. So you could have said, I'm going to let time be 3 seconds. I'll just put one passenger, 60 kilograms, instead of timesing by 20. You got the same answer. So I had some of my kids last block do it that way too. Yeah, fine. That's a pretty big electric motor. I was trying to think if these numbers are reasonable. I think my issue, 5 meters is a reasonable height. You know what? I think those SkyTrain escalators, which are the biggest ones, at least that I know of in the lower mainland, there's a couple of really, really long ones. I'll bet you those do have a huge electric motor with a high wattage. Or they might split it. They might have a couple of motors doing the work, which is much more likely now that I think about it. They probably have 3 or 4 motors splitting the work. How much work is required to stop a car? So work is force times distance. They didn't give me a force or a distance. Work is also the area under a force versus distance graph. They didn't give me a graph. Hey, work is also the change in kinetic plus the change in potential, except I'm assuming this car is on level ground, so no change in potential. Oh, and I had to change the 10 kilometers per hour. I had to divide it by 3.6, and I was lazy, Taylor. I did it right in the equation. What did the work? Which force? What stops the car? Friction. So I'm trying to think of ways that I could build on this question on your test, hint, hint. I could even then say, if I gave you the distance it took for the car to stop, could you calculate the average force of friction? Because you could now say 4,629 is equal to friction times distance. Oh, and once you had the average force of friction, could you calculate the coefficient of friction? Well, you'd need the normal force. I don't know the normal force. Oh, but look. If I drew my free body diagram right, I'm pretty sure that mg is the normal. I can even calculate what the average coefficient of friction. And I'm saying average because I suspect it changes a little bit over that long a distance in real life. But yeah, I could build on this quite a bit. Tarzan. So in A, how much work is done by friction? Now, because by the end of the year you'll have all sorts of approaches, Terry, what I said to myself first was, do you notice, is there a change in height?
Yes.
Is there a change in speed? Yes. Yes. Is there a yucky curved path? Yes. This is a job for a scalar conservation of energy. Okay, let me say that again. You ready, Terry? Is there a change in height from here to here? Yes. Is there a yucky curved path? Yeah. There's no way I would want to do this with vectors because the angle changes every split second that he's traveling. By the way, who's in calculus? There probably is a way to do it with vectors using calculus by defining the angle as an equation and building that into your actual formula. Ugh. Don't need to. We can use a scalar. So I said it's going to be the kinetic initial, potential initial, kinetic final, potential final. Whatever's left over must have gone into heat. I said you're starting at rest. I've been on a rope swing before. I said at the top you're at rest again. So I ended up with the heat being the initial potential minus the final potential. The reason you didn't get quite as high as when you started from is because you lost some energy to heat. How much energy? 74 joules. If there was no friction, what would Tarzan's velocity be at the bottom of the swing? Terry, is there a change in height?
Yes.
Is there a change in speed?
Yeah.
Is there a yucky curved path? This is a job for conservation of energy. It's possible I might be able to do this with Unit 1 stuff. Why bother bringing in vectors? So 7. Let's go on a roller coaster. So first part says, how fast is it traveling at the bottom? This question doesn't mention heat. Taylor, is there a change in height? Is there a change in speed? Is there a yucky curvy path? This is a job for conservation of energy. And they didn't mention heat, so I did that. I crossed out the masses. Sadly, not much was 0. Well, your final potential was 0. I multiplied everything by 2. When I did that, the half canceled, the 1/2 canceled. Oh, but the 2 does stay in front of the GH. In fact, what you end up with is VF squared equals VI squared plus 2AD. where A is 9.8 and D is the height, square root, and I ended up with 19.2 meters per second. Now, if you got the right answer, you get 3 out of 3, but if you got the wrong answer, this is what I would look for part marks. B, how fast is it traveling at the top of the second hill? Is there a change? It is a job for conservation of energy. Nothing canceled here. Nothing was 0. I did cancel out the masses, and because I had all those halves kicking around, Dorothy, I chose to multiply everything by 2, by 2, by 2, by 2, because here the 2's canceled with the half. Here the 2's canceled with the half. Here, I ended up with a 2. Here, I ended up with a 2, but that was still, to me, a prettier equation, less fractions. What am I trying to find? V final. So I minus 2GH final, and then square root, and I got 13.1. Okay. Can you give yourselves a nice, clean score? Now, I really screwed up because I forgot to put this quiz online, and I had some kids that were away that were unable to access it. So I'm not actually going to be collecting this quiz. Because you have your test on Friday, normally I would say, well, write your quiz down on a piece of paper. I'm not even going to write your quiz score on a piece of paper. Don't tell the people that are outside right now. I want to make sure that they think this was for marks, and I want to make sure that they will log on tonight and mark it, because I think there is some good studying that's going to go on with that for these human beings, okay? So that was for your own self-benefit and edification. So last day, and I forgot to check with anybody, who was away last day? Anybody? Because I didn't put the notes online, I forgot. I put the video apparently, but not the notes. And I didn't put the quiz online. We looked at power. Oh, and efficiency. Now for efficiency, I said my rule of thumb is it's always going to be the smaller number divided by the bigger number. You can't be more than 100% efficient. That's how I figure out the equation. Power, there was 2 ways to think about power. Power was work over time, which is how we initially defined it. And we also said because work is force times distance, you could also then say that power was distance over time, force times velocity, which we pull out once in a while. I gave you some questions to try. And so I will start out by asking, hey, any of these that you want me to go over, now is your chance to ask me. Number 6. I figured number 6. Number 6 is a nice question. Careful. I'm going to say I like this question. I'm not saying I like this. I'm saying, hey, this is a nice summary of almost everything. This is, to me, a good higher order. Let's make sure we know what's going on question. I'm going to cheat, if that's okay with you. I'm going to put number 6 right down here, and I'm going to copy and paste it, which is why I was opening up my background lesson already. Number 6. The lawnmower. So, Jason, if I'm visualizing this, I'm pretty sure we have free body diagram. Someone pulling up with 25 newtons. What are the forces acting on this lawnmower? Get the obvious ones. Darn right, gravity down. There's going to be a normal force. Jason, why did I draw it so short? Lifting up is taking some of the need for the normal force away. There's going to be friction. I do see a mu in the question. Now that's the free body diagram, except I'm going to add the horizontal and the vertical components of the lawnmower. Is that okay? A says find the work done by the person. Jason, the work done by the person, now work is force times distance. Here's the key. The lawnmower is moving in that direction. I better use a force that's in that level. Don't be using the 25. I'm going to be using the horizontal component, which I think if I do the quick trig with this being 15 degrees, I think it's going to be F applied cosine of 15 times distance. Is that okay? So it's going to be 25 times cos 15 times 4.5. And in fact, you may recall when we did the work lesson, I said the real formula for work is actually work equals FD cos theta, but if theta is 0 degrees, the cosine of 0 is 1, and you get force times distance. What does B want us to find, Jason? So I think the work done by friction is going to be the force of friction times distance. Friction is what times what? That's going to be mu times the normal force times distance. Now, you could make an argument that since we're in the opposite direction of distance, the angle is 180 degrees, and the cosine of 180 is -1, or you could just say we're losing energy. What's the normal force? I don't know the normal force. Oh, and I can't even say, look, there's another force the same size as the normal force. What I can say is, well, normal force plus vertical component equal mg. I think I can say, okay, the normal force is going to be mg plus, and the vertical component is going to be the applied times the sine of 15. That's what I said. As I said, it's going to be minus because we're lifting up, so of course the normal force is going to be smaller. Whew. I'm going to just quickly crunch the numbers. What was the mass? It was 20 times 9.8 minus 25 sine 15, and you get a normal force of, how about 189.53? That's a good one to round off to. So the work done by friction is going to be, what did I say mu was, 0.1? Normal force is 189.53, and the distance is 4.5. And that's where you get the negative because you're losing energy, 85.3. Now, Paige, if you had called this positive, because energy is a scalar, I would not take a mark off. What I would say, though, is if they ask you, what's the total work done on the lawnmower, you would have to say, oh, it's going to be the first answer from A minus the first answer from B, or plus negative the first answer from. Just clue in that some of the energy has gone into friction, and so the total work done is smaller than the amount of work you're doing. However you choose to clue that in. Okay. You okay with that so far, Jason? Oh. Could have told me that, yeah. What are they asking you to find in C? You know what? If I can find the acceleration, I think then I can go and I can solve for T. How am I going to find the acceleration? Last unit. In fact, I gave you a lawnmower question on your test last unit, which we're going to be going over in class in just a few minutes. Who's winning? Fx. Who's losing? Friction. So you're going to go winner minus loser equals ma. The acceleration is going to be Fx, which was 25 cosine, I think. Yes, Jason? Minus friction, which was mu times the normal force of 189.53 divided by, what was the mass, 25? 20? 20. That should give you the acceleration, and that should work. Did you try that?
I already saw it.
Oh, okay. And then go from there. That should get you there. Okay. I probably wouldn't ask that on this upcoming unit test, this fine time. In fact, I'm fairly sure I threw a bunch of those at you on your last test. I gave you, by the way, instead of the lawnmower question like this, I put it on a ramp, but there was still an angle and it was still sliding and you still had to find components, right? Is that okay? Yeah? Any others from the homework? Number 4. Good, you guys are asking the same 2 questions that my last class did. Probably means they're good questions. Or it means you guys are really, never mind. Let's assume they're good questions. You know I like you guys. Well, the 5 of you that didn't do your quiz, okay. I'm going to gulp. By the way, I've really debated on these handouts, leaving you room to show work on the handouts and not. My photocopy count is through the roof on this. So the first year I did this, I actually included workspace, and it was just a disaster. I went through several 100,000 copies. So we're not going to do that anymore. You can write on a piece of paper or write small. And there's the block, and I'm going to draw it. What are the forces acting on it? Get the obvious one? Yep. Normal force, yes? Now, the key concept here is that we're at a constant speed. Something is pulling it up the hill. And you know how big that something is, Paige? It's exactly the same size as what's pulling it down the hill. And what's pulling it down the hill? Because it doesn't talk, frictionless. Okay? So what force is required for part A? I think it's going to be, which two lines is sine? We can thank Cole in my other class for that. It's going to be mg sine of 25. That's how big the force is if you want to pull it up at a constant speed. B. What does B want me to find, Paige? Power, which we defined as work over time. And that's going to be force times distance over time. Oh, they didn't give me a distance. Ha! Those sneaky little people. That's why they gave me, they didn't just say constant speed. They actually told me the magnitude of the constant speed. So it's going to be force, which force? From A times speed. That's how much minimum power is be required, because in real life there would be friction. That should get you there. Nice. That's a tough question, but when you see it, suddenly you're like, now I see why they put that together that way. I hope. Any others? So if I go in a tutorial today after school, who's planning on coming by? Okay, so I will be here. If I'm not here right away, just have patience, because I'll have to, it's really going to depend on how long the basketball game lasts and goes, and I hope to be here. Okay? And sorry I can't go tomorrow. You're before lunch, so I can't go at lunch on Friday, and I have a meeting tomorrow at lunch. Otherwise, I'd offer to go at lunch tomorrow. Anyways, this is my week with no life or schedule. Any other questions at all? So if you want to hand in the power homework, you can, or if you want to hand it in on Friday because you've written your homework on the notes and you want to hang on to the notes, I'm fine with that too. I'm not going to be entering any homework until this weekend. I'm not going to be marking the tests until this weekend anyhow.